Today's topic is intermolecular forces of attraction. It's a mouthful. We'll short form it to IMFA, which isn't really any easier to say, but a little bit easier to write. Okay, what is it? Obvious question. It's, again, not a very imaginative name, but it's exactly what it says. It's the force of attraction between molecules, two different molecules that aren't the same, you can read, okay? Between two separate molecules. So it's intermolecular force. Can be molecules of the same type or a different type, so it can be a solute solvent, or it can be two molecules that are exactly the same, two water molecules. Okay? It's not holding a molecule together. Those are forces of attraction between two nuclei and electrons at the same time, and those are different. They're sometimes called intramolecular forces, but we don't really care about that. We call them bonds. Okay, so if I have two molecules, and these two molecules are the same type, the intermolecular force is not between, the solid sticks. It's not solid sticks. It's in between two molecules. Now we rarely draw those in. Sometimes just sort of to illustrate a point, we'll draw them in. But we have to understand whenever we see a chemical formula, we're representing lots and lots of them, and they might be interacting with each other. That's an intermolecular force. So if I put two molecules side by side and have them look like this, so you can see the bond, solid line, you can see the dashed line, that's the intermolecular force. The bonds, generally speaking, are very strong compared to the intermolecular force, which is very weak. So why do we care? Because sometimes it matters, because if we're talking about structure determines properties, properties include things like solubilities and melting points and all these other things, and that will be influenced by intermolecular forces. So they are really important. In fact, a lot of the things that we can see day to day about compounds and things like that have to do more with intermolecular forces than with bonds. Although intermolecular forces have to do with bonds. And bonds have to do with, and it goes back in structure determines properties. That's been our whole theme. Okay, it might not sound that simple, but we're going to say that so that you are reminded of that. Okay, all particles can have intermolecular forces of attraction. They won't be the same from one to the next, but they can all happen. Mentioned that already. Okay, now some of those forces are really weak, and some of those forces are really strong. It's like having, masking tape versus duct tape or something like that. They're both tape, but they're not the same. And you can have very strong forces. Okay, think about states of matter. Solid, liquid, gas. Too easy. What is it that keeps the particles of the solid in that state? What is it about the particles of the gas that allow them to come apart from each other and float all over the place? What about, it's temperature? No, it's not, because you can have a solid at room temperature, and you can have a different material that's a gas at room temperature. So same amount of temperature, same amount of heat energy, but one has particles flying all over the place, the other has particles stuck together. Okay. Or you can take a solid and you can heat it up and you can make it a liquid. Oh, what's happening when you do that? Oh, you're heating it up and the particles are moving faster. So what? They're moving faster. All of a sudden they break away from each other. Think about that. So we actually kind of have a handle on some of these things already. Okay, let's start with the forces, and we're going to start with London forces. It has nothing to do with London, England, or London, Ontario. It's named after a person. It doesn't really matter. Everything can do London forces. And London forces are a little bit on the weird side, but they're also very weak. Now, sometimes we can ignore that, and sometimes we can't ignore that. Now, if you have a nonpolar molecule, then London forces are it. London forces, so then we can't ignore it. But London forces are going to be the thing. So, how do London forces happen? Nonpolar molecules, you're going to end up with sharing of electrons, usually a fairly equal sharing of electrons. Okay, so there's no positive portion, no negative portion in the molecule. But you can have, as these electrons are moving around, you can have, the electron is now over here and is not over there. So if I show you a picture of a molecule, not a very well drawn molecule, but look at where the electrons are, look at where the electrons aren't. Okay, now, right now, wherever those electrons are, there's a slight negative spot on that molecule, and where the electrons aren't, there's a slight positive part. And if I put a few more in there doing the same kind of thing, I now could have a very momentary, very instantaneous, very short-lived force, because yes, those electrons keep moving around. So that's one of the reasons why those forces are very, very weak, is how they happen, but also how long they happen for. So as those electrons are moving, the location of that partial negative, of course, is moving. The location of that partial positive, of course, is moving. So they never really get to line up and stick. And if I were to have bigger molecules, similar kinds of things are happening just because the electrons are always moving. Dipole, dipole. Well, dipole just means two poles. We don't have very good names, but they're descriptive. Okay? If I have two polar molecules, they don't have to be two polar compounds, just two polar molecules. And now I've got a partially positive that sticks around, and I've got a partial negative that lasts a little bit longer. I can still have those electrons moving, so I still have London forces, but now I've got a longer-lived polar end, partial positive end, partial negative end. Okay, so now I've represented it this way, and you can see how those things could line up and stick together a little bit better. And something like this. Okay, so well, let's just move on then. I mean, real molecules, whether or not they end up forming the triangle thing like that, it's pretty unlikely. And those forces are still not, I'm using the word stick. They won't necessarily stick forever, right? Those things can break away. Think about the a liquid or something. Particles can move around fairly readily. Hydrogen bonding. There's a couple things you need to know about hydrogen bonding. Thing number one is it's not a chemical bond. Okay, so I know I've been saying that chemistry doesn't have very imaginative names with their descriptive names. We blew it. Okay, we did not pick a good name for this. It is not a chemical bond. Second thing that you need to know about it is it has very, very strict criteria. So just because you see a hydrogen does not mean hydrogen bond. What does it have to have? It has to have a hydrogen bonded to a nitrogen, oxygen, or fluorine. Those are your more electronegative elements. What about chlorine? No, the hydrogen has to be bonded to a nitrogen, oxygen, or fluorine. And then you have to have one of those atoms next door, on the next molecule over. Okay. So, would this work? Well, yes, for here, because I have a hydrogen bonded to an oxygen, and then I have an oxygen next door, but not there, because that oxygen next door, yay, hydrogen, but not bonded to an oxygen or nitrogen or fluorine, bonded to a carbon. Doesn't work. So hydrogen bonding somewhere, not somewhere else. And for there, yes, because I've got the nitrogen next door, I've got a hydrogen bonded to an oxygen, and this one also would work. Okay. So make sure you can recognize when hydrogen bonding can happen. It's possible that hydrogen bonding can happen in more than one location. If you look at, if you look at the two green molecules, I've got a hydrogen bond on one that I don't have on the other, but I could. I just didn't draw it in there because I'm efficient like that. Okay, leaving you with some questions. The big one is, so what, right? Structure determines properties. So how is this going to affect? Okay, so now I've got a little bit more about structure, a little bit more about properties. Okay, that's going to be a big important question for us to be answering as we go through this. And we won't have final answers even by the end of the week, by the end of the course even. It's going to be a big thing that hopefully develops. And I kind of would love it if you, in the back of your mind, started looking at things around you in terms of structure determines properties, in terms of what you know about chemistry, in terms of intermolecular forces of attraction. What if you have a lot of London forces? Remember I said masking tape versus duct tape? Well, what if I took a whole roll of masking tape and wrapped it around something? Would that be as strong as a duct tape? I don't know. Try it with something. What happens if I mix molecules of different, that can do different types? Throw in some London forces with some dipole-dipole, maybe something that can do hydrogen bonding. What if I have them all in there together? What's going to happen? Are they going to mix? Are they not going to mix? Things like that. So there's lots of things that are going to be involved in this. But we'll start sorting these things out in class, and we'll talk to you then.